Let's now take a look at nuclear chemistry. This is indeed a totally different animal. Remember earlier in chemistry, we would tell you, you can't gain or destroy matter. That's why you have to balance a chemical equation. But I would throw in, kind of under my breath, in a chemical reaction. And when you did thermodynamics, well, the heat loss has to be equal to the heat gain. Why? Because you can't lose or gain energy in a chemical reaction. Why the disclaimer? Because it's not universally true. In fact, in nuclear chemistry, we do destroy mass and we do create energy. And because it's so very different, that's one of the reasons it's the last chapter that we're going to cover. So let's look at this fascinating world of nuclear chemistry. Houston, we have a problem. Not all nuclei are stable. And we know that from things being radioactive. What's the remedy? How does Mother Nature handle nuclei that are not stable? Well, she does a couple of things. If there's a real big atom, then she might break it into pieces and make smaller atoms that are more stable. Or she might take some really small nuclei that are unstable and go through a fission process and fuse them into a large molecule that's more stable. As with traditional chemistry, it's all driven by Mother Nature trying to reach the most stable state. Well, before we get too deep into it, let's look at some just basic terms that we need to know when dealing with nuclear chemistry. First, let's harken way back to early in your first semester Gen Chem 1411, to where you had a symbol that looked like that, and you remember that the total number of protons and neutrons is called atomic mass, and that's given the symbol A, and the atomic number is just the number of protons. It usually represented, that's where we count the positive charges, and that's called atomic number. And now what we're going to do is, before in chemistry, we've largely followed the electrons. That was it, right? You follow the electron to see what happens. If you follow the electrons, you can tell if something is going to be positive or negative. And that way we can see if it's going to be an ionic compound. Or you follow the electrons and you can see if something is going to be oxidized or reduced. Earlier, we focused on the electron. In nuclear chemistry, needless to say, you're going to focus on the nucleus. So let's kind of look at this nucleus thing. The first thing that you need to know is relative to the size of a molecule. The first thing you need to appreciate is that relative to the overall size of an atom, the nucleus is very, very small. There's a lot of empty space out there. So for example, if you take a gold atom nucleus and you expand it so that the radius is about 1 foot, then the outermost electron would be about 3.3 miles away. Yes, make it about the size of a basketball and your outer electron is over 3 miles away. That's a lot of empty space. How much empty space? It's even more empty on a percentage basis than our solar system. Take the sun and shrink it down to where it's about 1 foot wide. From the sun to Pluto would only be 1.6 miles. So on a relative scale, there's a lot more empty space in an atom than there is in our solar system. But nevertheless, even though it's mostly empty space and the nucleus takes up a very, very, very small part of the atom, it's still tremendously important. Well, let's look at the nucleus another way, the density. The density of a nucleus is about 1.8 times 10 to the 14th grams per milliliter. Well, how packed is that? Okay, if the Earth has the same mass as it does now, But if we made the density, if we compressed the Earth, took the ball and just pressed it in and compressed it until Earth had the same density as the nucleus, the Earth would only be about 200 yards wide. So the nucleus is extremely dense. So let's take a look at three terms we're going to need to be able to differentiate to talk about nuclear chemistry: isotopes, nuclides, and nucleon. Isotope, we're familiar with what those are. We worked with those last semester. What's that? That is any species that has the same atomic number but a different atomic mass. These are isotopes of carbon, and here's two isotopes of nitrogen. But I would really like a catch-all term that would include any isotope from any type of element. And those species are called nuclides. And they represent any isotope that has a set atomic weight and a set atomic mass. And what's a nucleon? Well, we're going to talk about protons and neutrons, and we want a catch-all term that refers to either one of those, and that term is nucleon. Now for the big curious question. What holds atoms together? We're going to follow that right with the question when we were studying quantum mechanics of why, if the nucleus is so positive and electrons are negative, why don't the electrons just fall into the nucleus? That's a good question. And the answer wound up being, well, because quantum mechanics doesn't allow it. That's about as best we can do. It just mathematically, it doesn't happen. Schrodinger said it doesn't fall in there, and so it doesn't. So, returning to the nucleus, let's see if we can get a handle on what's going on. So let's talk about the four types of forces, because that is one of the four. First is electromagnetic, which you're very familiar with. Yes, opposite charges attract. Gravitational forces, we're familiar with that. The weak nuclear force. So this is what binds your atoms into molecules. And the strong nuclear force. That's our mysterious force that holds the nucleus together. So, what do we have here? Although on a very small scale, we have the two most powerful forces in nature are at a tug of war. We have the strong nuclear force, as it were, pushing in, holding the nucleus together. And we have all these positive charges, these like charges, these electromagnetic forces that are trying to push it apart. And sometimes the nucleus does actually break apart. And that's where the world of nuclear chemistry lives. Well, it may not be intuitive as to what actually holds the nucleus together, but we can perform calculations to determine the strength at which it is held together. So let's see how we can figure that out. First of all, we know about how much a neutron weighs. 1.008664 atomic mass units. And a proton is just a little bit lighter, just a small amount lighter, 1.007 AMU. Well, how could we measure the energy? Well, let's see. If we make an atom and we add up the weight of all of the protons and neutrons, we come up with a certain value. And when we actually go in and measure the mass, we find out that the mass is actually different. There is a loss of mass. Can't create or destroy matter? We just did. Why? Because this is not a chemical reaction. This is a nuclear reaction. Well, that told us about mass. How does that relate to energy? We're interested in how much energy is holding this thing together. That's where Albert comes in. And his famous equation, E equal mc squared. So what does that do? That relates energy to matter. In other words, it tells us if you have a certain amount of matter and you convert it to energy, that's the equation that you use. Now this term winds up being very, very big, as we know that from nuclear reactors and nuclear bombs and those sorts of things. We know there's a lot of energy tied up in just a very relatively few nuclei. Why so big? Well, what are you multiplying mass by? The speed of light, which is a really big number, and you're going to square it on top of that. So what this equation basically tells us is a little bit of mass being converted to energy is going to make a lot of energy. Well, let's look at the mass change. If we have a mass change, we have an energy change. And this energy change is the bond energy. That is the amount of stability. That's the amount of energy that we're using to hold our nucleus together. And this delta mass is called the mass defect. And in this case, we did a simple calculation and a measurement. And we know what delta M is. We know what the speed of light squared is. We can calculate the binding energy. Oh, by the way, one conversion factor we're going to use a lot later is electron volt. Joules is just a very, very huge number. And so, because these are relatively small when we look at individual atoms, and we're going to report some of these values in terms of individual nuclei, then those numbers tend to be pretty small. And so we're going to use electron volts. And there's your conversion factor from those. Well, let's take a sample problem. What is the binding energy for the high helium atom in mega electron volts? Remember mega? Mega is what? A million of something. In mega electron volts, giving the mass defect is 0.0305 AMU. And it gives you a conversion factor that if we've used it, we haven't used it much. So let me kind of remind you of that because that's going to be very, very important. It's very clumsy. It's very clumsy looking. A kilogram meter squared per second squared. That's not real intuitive what that is. It's pretty easy to understand what a joule of energy is, a joule of heat. And here it is kind of typed out so we can use it. It kind of has it clean. Okay, so let's go back. Binding energy, what do we know? The binding energy is equal to delta M times C squared. Well, guess what? We're looking for this, so I'll box it. One equation, one unknown. Do we know delta M? Given, do we know C? Yep, that's a constant. About 3 times 10 to the 8 meters squared per meters per second. That's the speed of light. About 3.8 meters per second. Okay, so that's a given constant. There we go. We have no unknowns. We plug in our numbers, and we wind up with 2.74 times 10 to the 12th kilogram meters squared per second squared moles. Okay, well, that seems really clumsy until once again we recognize, oh, we've got kilogram meters squared per second squared. That we'll just replace that with a joule. And so now this feels a lot more comfortable. There's that many joules per mole of helium. Are we done? No. Why? Because it's specifically stated in the question, I want the unit of energy to be mega electron volts. And I don't want you to report it per mole, I want you to report it per nucleus. So now what we have is a simple conversion factor. We have a first semester, if you will, conversion factor. So what are we targeting? Mega electron volts per nucleus. We write the answer that we started with. We're going to start with that. And let's see what we're going to do. We're going to convert joules to electron volts using our conversion factor. And then we're going to convert electron volts to mega electron volts. And that's the first one. I like that. What do I have as a unit in the denominator, in the numerator? Mega electron volts. And what am I looking for? Mega electron volts. So I'm pleased with that. How about the other one? We're going to go from mole to nuclei. I know in 1 mole of anything, there's 6.02 to the 10 to the 23rd of those things. And a nuclei is a thing, so Avogadro's number will work. So when we multiply that out, we wind up with 28.4 mega electron volts per nuclei. And now you see why we tend to deal with mega electron volts. Because when we start dealing with individual nuclei, it's a number that's pretty manageable. It kind of puts it on a scale that we can easily comprehend. Fortunately, there are some indicators that will tell us which nuclides are more stable and which are less stable, and hence most likely to undergo degradation reactions. Well, there are some general trends. One of the general things is there's literally thousands of different types of nuclide and only about 250 of them are stable. So most of the nuclides that we see, they're going to be unstable. So here's some general empirical observations that have been made. A band of stability has been defined looking at the neutron to proton ratio of the different nuclides. And that's shown in the green band there. And as that ratio of neutrons to protons strays either to the high side or the low side of that band, it might undergo degradative reactions in the effort to move back into the band, back into that green zone. There are, however, some species that are particularly stable, and they're identified by what are known as magic numbers. Okay, so we can find some of them here, and let's see, what are the magic numbers? They are numbers in which the number of protons or neutrons or sum of protons plus neutron equals one of the following: 2, 8, 28, 50, 82, or 126. So now we have an indication of what stability is. It's in the green band, and we've even have an indicator for some that are really stable. But if they're not stable, what if we wind up with an isotope that's, a nuclide that's, say, way out here, or one that's over here, or one that's down here, pretty far off the line? What's Mother Nature going to do? Well, she's going to get involved in that radioactive thing. She's going to start throwing out or taking in subatomic particles to try to move the nuclei back into the green zone of stability. Well, what do you mean subatomic particles? Okay. In general, now there are dozens of subatomic particles, but here and so far in this course, we've only been interested in 3: protons, neutrons, and electrons. Well, we're going to expand that just a little bit, not near to the full aliquot of subatomic particles, but we're still going to expand it to 6 key particles that we're going to use to move species that are off of this band of stability into the band of stability. The first is a beta particle. It's something that has negligible mass, and it has a charge of -1. So what is this really? Okay, so we can think about it as being an electron that's living inside the nucleus. Okay, it's not one of the electrons floating around out there near Pluto that we saw. This is you can almost think of this as being an electron that's living in the nucleus. All right, so that's a beta particle. Okay, here's a weird one, a positron. It's like an electron with a positive charge. And so we'll kind of draw it. You can draw it like that if you want. And then there's the alpha particle. Well, that's no big deal. We know what that is. That's just a helium nucleus. It's got 2 positive charges and total mass of 4. The next species on the list is our old friend, the neutron. And that has what? A mass of 1 and a charge of 0. And yet another familiar face, the proton, which has what? A positive charge of 1, and it also has a mass of 1 AMU. And finally, there's this thing called gamma. It has no charge and it has no mass. It is essentially raw energy. So in light of those 6 particles, let's have a look at our diagram again. Now that I've really boogered it up real good. All right, so what do we have if a species is here? We have too many neutrons, yes? Basically, our neutron to proton ratio is too high. So what do we need to do? We need to make more positive charge, protons, and we need to take away the neutral charge, the neutrons. And we could do that with beta emission. So what happens every time that happens? What are we losing? If you take a beta particle and you sling it out of your nucleus, what are you losing? You're losing a negative charge. So what's happening? Your neutral species are becoming positive charged. So every one of those you use, you're stepping closer to this. You're losing ends and you're gaining protons. And so you're moving, actually moving that direction. You're moving toward the line. And so what happens if we have a species down here? Well, essentially have what? We're too low on this diagram. We don't have enough neutral species to make the ratio up. Or you could look at it as if we have too much positive charge. So how could we do that? Well, first thing we could do is we could do a little positron emission. We could get rid of some of our positive charge. Yep, so we just take some of the positive charge and we throw them out of the nucleus, beta emission. Or we could maybe capture some negative charge. So if we capture negative charge, what happens? Our protons now take a negative charge and they now become neutrons. And so you can kind of rationalize using this diagram and either the emission or capture of these subatomic particles. You can see how we can move species off of the band, out of the band of stability into the band of stability. And so let's take a look at a few of those reactions. Here's an example where the neutron to proton ratio is too large. So what do we need to do? We need to make more positive charge, hopefully at the expense of something that's neutral charge. In the radioactive decay of radium to actinium, radium-288, it will eject a beta particle. It throws out one of the negative charges, so what does that mean? Something that's neutral now becomes positive charge. And so we move into the band of stability, or at least closer to it. By the way, I do want to mention something that's really important when you work with these nuclear equations. Notice that the amount of material does not change. That you're going to have across the top the same nuclide mass. And also look at what happens here. Your charge remains constant. Well, here's an example of one where your nucleus to proton charge is too small. So what do you need to do in that case? Well, you probably need to get rid of some positive charge. And we do that with a positron loss. So here potassium is going to argon, and you can see that our positive charge here has dropped from 19 protons to 18 protons in argon. And finally, a general comment that all nuclides with a atomic number greater than 84, they're all radioactive. So this is a good example of just how subatomic particles are manipulated to bring species back into line with the stability series. So here's a couple of questions here. Which of these is more stable? Can you tell just by looking at these? And the answer is, yeah, this is a pretty easy one. Why? That's one of your magic numbers. So you know that's unusually stable. Okay, let's see what we could do here. We've got a question here where magnesium 26 is going to aluminum 26, and I note that it gave off a neutron. Balance that chemical equation. We know the mass has to even out, so if it's 27 on one side, on the product side, it's got to be 27 on the reactant side. Looking at the mass, we have a total of 27 on the product side and only 26 on the reactant side. So we need some species that's going to contribute 1 AMU to our mass. Looking at the charge, we see the total charge on the right-hand side of the equation is 13. And we have on the reactant side, as it now stands, magnesium has 12. And so we need a species that also has 1 positive charge. And there's only one subatomic particle with a charge of 1 and a mass of 1, and that is a proton. How about argon to potassium? See if we can figure out what this is. Okay, so we're going, what do we have? A total of 44 on this side, total mass, and we've only got 40 here, so it must be something with a mass of 4. And now let's look at the bottom here. We've got a total of 18 positive charges on this side, and we have, let me see, so what is potassium? You look it up, and that's actually 19. I can look that up on the periodic chart for a total of 20. And this is 18, so it must be some species that has a weight of 4 and 2 protons. And it must be our alpha particle. What is the binding energy for helium per nucleon? And sometimes the data is reported in per nucleon. So read the question carefully. If it's per mole, or per nucleus, or per nucleon. Now, I'm not going to go back and work all that we did earlier, but earlier we actually dealt with a helium nucleus, and we had determined that it was 28.4 mega electron volts per nuclei. What does the question ask us? For mega electron volts per nucleon. Well, I already have the numerator in mega electron volts, but that was per what? Per nuclei. So what do I have to do? I have to convert nuclei to nucleons. And in this particular species, how many nucleons do we have? 4. Therefore, I'm going to have to divide this by 4, and I wind up with 7.10 mega electron volts per nucleon. Can we get an indication of which direction our nuclear reactions are going to go? Are we going to undergo fission reactions, where we're breaking larger atoms apart into smaller atoms? Are we going to undergo fusion, where we have smaller atoms being combined? Well, looking at the energy curve, we can see that the most stable species happens to be iron. If you look at the energy curve here, the binding energy is greater for iron than anything else. What this basically says is that's going to be your most stable configuration. And so other elements that are not stable are going to tend to go toward the iron stability, toward the most stable species they can make. So that's a binding energy curve there. So let's see what that might look like. Let's calculate the binding energy per nucleon in mega electron volts, fine, for iron 56, given that it has an atomic mass 55.9349 AMU. Okay, the first thing we need to do, if we're going to get at binding energy, I bet we're going to need to know our mass deficit. So let's see if we can move in that direction. First thing we need to know is, what's the mass of all of the pieces that we're going to use to make the atom? Well, we know we're going to use 26 protons, and we know how much each one weighs. And we're going to use how many neutrons? Let me see. A minus C. Oh, yeah, it was equal number of neutrons. And so we have 30 neutrons. So we put all those in a basket and we weigh them. 26 things that weigh this much, 30 that weigh this much. We do the math and we wind up with 56.4651 AMU. is what's in our bucket. But what did we just say it actually was? It was actually 55.9. We calculated 56.4. Hey, we just lost half an AMU. Where'd it go? Easy. It turned into energy, and that's what's holding our nucleus together. How much energy? E equal mc squared. We know m. We can convert AMU to kilograms. So now we have our weight in kilograms. Why are we going to kilograms? Because I know I'm going to need to target this unit so I can convert it to joules. Not grams, not AMU. I need to get to kilograms. By the way, it is a tripwire where people will actually convert it to grams and they'll work from that. Don't do it. This unit specifically requires kilograms. So I'm going to convert AMU to kilograms. And then what? Multiply it by the speed of light squared. So if you square the number, 3.8 times 10 to the 8th meters per second. If you square the number, you have to also square the unit. And when we multiply all of that out, we wind up with 7.9 times 10 to the minus 11th kilogram meters squared per second squared, which is the same as joules. Oh my, but that's for the atom. That is for an atom of iron. It asks for how much for the what? Per nucleon. Oh, yes. It asks how much per nucleon. So what do? It's a simple conversion factor here. What are we going to do? We're going to convert joules to mega electron volts. We're going to make those work out. And then we're going to convert atoms to what? Nucleons. There's 56. Yes, right there. So we know that the atomic mass is 56. There's 56 nucleons for every atom of iron. And so we wind up with 8.820 mega electron volts per nucleon. Are we buying that? Sure we are. Why? Because we just looked at iron and we said it's the most stable. And we look at the value and sure enough, it's in between 8 and 9, just looking at that crudely on the graph. And that's exactly what we calculated, 8.82. So we have just proved that that is on that part of the graph. And you'll have to take our word for it, that if you did the same calculation for all of these others, it would be less than 8.82 mega electron volts per nucleon. And so let's look at just a few examples of nuclear equations that are pretty well known. Madame Curie, right? One of your pioneer workers here in the area of radioactivity. She studied polonium, the degradation of polonium giving off alpha particles. Of course, they didn't know quite how dangerous radiation was at the time, and I think she might have hurt herself just a bit with it. But she did fantastic work, and by the way, this compound polonium is named after her home country of Poland. James Chadwick, you may remember him when we studied these subatomic particles. We talked a little bit about Rutherford, and we talked about J.J. Thomson and about these people who discovered what the atom was comprised of. But when we got to who discovered the nucleus, we just kind of said this guy named Chadwick discovered the nucleus, and we just kind of brushed on by that. Didn't talk a lot about his experiment. Well, the reason is it was a nuclear reaction. It was a little early in your chemistry career to be talking about nuclear chemistry. So essentially what he did, though, is he did the beryllium experiment and he did a nuclear reaction, and there you go. Wow, there's the neutron. It showed up. It's really in there. Ernst Rutherford, we remember him, yes. Okay, the gold foil and all of those types of things, yes, and he was bombarding things with alpha particles. He did more than just that. He didn't happen by that experiment. He was one of the first, he was the first to actually prepare a radioisotope. Not just dig it up, but actually prepare it by artificial means. Another rather famous reaction is the first controlled chain nuclear reaction. That was a reaction in which uranium-235 was bombarded with neutrons. And I think the operative word here is it was actually a controlled chain reaction. Okay. And so with that, hopefully you have a good feel now for kind of what this nuclear chemistry game is about, and you're able to contrast it with the chemical reactions that we've done for the prior year. That's it for now.